Okay, this is what I wanted to get to. Okay, doing the method of initial rates. Okay, so this is a very classic way of determining a reaction order. So not only the reaction order, but also determining the value of the rate constant. Okay, and you actually did this in Chem 110. If you took Chem 110 at HSU, you did this. This was the clock reaction using, you used yeast, and what else did you use? Peroxide disulfate as an oxidizing agent. Now I'm forgetting that whole reaction. But anyways, you did it in Chem 110. And so here's how that works, okay? So when we look at this reaction, 2I atoms plus argon makes I2 plus an argon atom, okay? And this is a rather obscure reaction, so let's not worry about that for the time being. I just want to use the data from this reaction. The first thing we would do is set up our generic rate law. And we would just say rate equals K times reactants, so times I raised to some power that we're going to try to figure out. I'll just use the letter X. And then times the other reactant times argon, and it's going to be raised to some power Y. And again, we have to use experimental data to figure out what those values are. And if you think about this now, we have one equation with two unknowns, which actually means we need as a minimum 3 experiments, okay? So we need to be able to, in 2 experiments, hold one value constant while we let the other value vary, and then flip that. So that gives us 3 experiments, and you're gonna see that now, okay? And so the way that I can do this, the way I can start systematically figuring these out via this method of initial rates is by doing the following. So if I pick a set of data, so for example, I'm going to start with this first rate of reaction, okay? And I'm going to write that down. I'm going to say that's 3.48 times 10 to the minus 3, and that was molarity per second, okay? And so I recognize all of that equals K times concentration of iodine times concentration of argon, okay? So now for this reaction, so the way I set up this table, okay, this rate resulted when we had, let's see, 2 times 10 to the minus 5th of iodine here, and 1 times 10 to the 3rd of argon. So that's how my table works, all right? So this rate is involved when argon stays the same, but now when the iodide is cut in half. So now I'm just going to plug in those values. So I'm going to plug in, let's see here, 2.0 times 10 to the 5th, that's molarity, and it's raised to some power. And then I'm going to plug in the argon, which is down there, 1.0 times 10 to the minus 3rd molarity, Y. And now what I'm going to do is divide this whole equation by another set of data, okay? And the set of data that I'm going to pick is I'm going to hold one of these constants. So let's hold the argon constant. And when I hold the argon constant, I have to vary the iodide. So that gives me to this experiment right here, okay? So now that's 8.70 times 10 to the minus 4 molarity per second. And that equals K. And now my iodide is 1.0 times 10 minus 5th molar, okay? And now my argon remained the same, 1.0 times 10 to the minus 3rd molar times Y. And so now the way this works, okay, K and K cancel. Let's see here. So 3.48 divided by 0.870. So I just dropped the exponents there. And you should work this out on your own for sure as well. So that all equals 4, okay? K was canceled, but you can see now 2 times 10 minus 5 divided by 1 times 10 to the 5, all raised to the x power, is just going to be 2 to the x power. And now 1 times 10 minus 3 to the y divided by 1 times 10 to the minus 3 divided to the power y, that all cancels. So as you can see, this is a perfect experiment. So x equals exactly 2. In a real experiment, you know, your rates might not come out to like a real nice rounded number, but reaction orders are whole number integers, okay? Reaction orders are whole number integers. So that means we know that the order of iodide is 2. And we're going to talk about what that means in a moment, okay? Now when I want to go to do the next one, so I've got to figure out why. And so now I need to look at data in which the iodide concentration remains the same, but now the argon concentration varies, okay? And so here's the one I picked. I'm going to do that 8.69 times 10 minus 3 molar per second, okay, equals K. And so this one resulted when I have this concentration of iodide and this concentration of argon. So now that's 1.0 times 10 minus 5. But I already know that that's raised to the second power for the second order because I figured it out up there, okay? And then now the argon is 1.0 times 10 minus 3 molar raised to the y power. And now I'm going to divide that one by this 4.35 experiment, okay? 4.35 times 10 minus 3 molar per second equals K. And you can see now why we do this systematic variance, because now I can knock out iodide from the equation, all right? And now, oh, you know what? That says 10 times 10 to the minus 3. Haha, maybe you caught that, maybe you didn't, but I just caught that. This is 10 point times 10 minus 3. And now this one is 5.0 times 10 minus 3 molar, all raised to the y power. And I can definitely do this one in my head. 8.69 divided by 4.35 is 2, okay? And the k's and the k's cancel, and this cancels. And then now what I'm left with is 10 divided by 5 raised to the y power, which is just 2 to the y power, so y has to be 1. So what does all of this mean now? Well, what this means now, my rate law equals K times iodide to the second power times argon to the first power. So what we would say is the reaction is second order in I, it's first order in argon, and it's third order overall. So let's write that actually where I left all these blanks here. So if we had a reaction that looks like this, right, that data that we just did, okay, we would say it's second order in I. We would say it's first order in argon, and 1 plus 2 is 3, so we would say it's third order overall. And we're going to see the consequences of this in the next video, all right? So let's see here. Or like another one, let me just back up. Now I think I know why I had all this other stuff. So to give you another example, if I just said now, so let's suppose that a rate equals K times A times B. So let's suppose it worked out like that. And when I don't write a number on the exponent right there, it's implied that it's raised to the first power, right? So if I had one that looks like this, it would be first order in A, first order in B, and second order overall. Okay, so they all add up. All right, great. So that's 30 minutes. To me, that's a pretty good amount of time for this first video. So in the next video, I'm just going to be going one by one through what is a first order reaction, and then what is a second order reaction. So those are the main two that we're just going to stick with for this initial section. But then eventually we're going to start looking at the weird ones. Like we're actually going to see examples when there's half order reactions. So more often than not, these reaction orders are whole number integers. But of course, because chemistry is the science of exceptions, There are times, there are some exceptions to that when we get these weird half-order reactions. And we're also going to talk eventually about a zero-order reaction. Okay? So we'll get there eventually, but for now, for this intro chapter, we're just going to stick with first-order reactions and second-order reactions and what those look like. Okay, folks, I'll see you in the next one.